In this video, we're going to look at equations of lines. And in the first half of the video, I'm just going to take a line algebraically, and we're going to write down the point-slope formula for the equation of a line. And then in the second half of the video, we're going to look specifically at the tangent line to a function where we can use a little bit of calculus and put that calculus into the point-slope formula for the equation of a line. All right, so I've got some line here, and to figure out the equation of it, I'm going to need two pieces of information. The first is, I just want to have some particular point that's on the line, and I've chosen to put an x naught, y naught, some point where I might know what it is, and in this case it looks like the point 1, 0. You could choose any point on this line, it's just convenient to get one that you know. And then the second piece of information I need to have is I need to have the slope of this line. And my claim here is if I know what the slope of the line is and I know some point on it, then I can write down the point-slope formula for the equation of the line. All right, how do I do that? Well, to figure out an equation, what I'm trying to do is I'm trying to figure out what all the other points are. I've got this one which is on here, but I want to come up with all of them. So let me put this second point here, and this time I'm going to denote it by x, y, and I think of x, y as they're my variables. They can move around. The x naught, y naught is just one specific fixed chosen point. Now the idea of slope is this. Between the xy and the x naught, y naught, there is a little bit of rise and a little bit of run. There's a little bit of change in x, a little bit of a change in y. We often use this symbol delta x and delta y here to denote this change, but it's just the difference in the x values or the difference in the y values. Then the slope is the rise over the run, or in other words, it is the change in y divided out by the change in x. In other words, it's y minus y naught over x minus x naught. And then the last thing I'm going to do before I finally have my point-slope formula is that I'm just going to go and rearrange this expression, and I'm going to bring the y minus y naught to the one side and say that this is equal to m times x minus x naught, and there is the point-slope equation of a line. So the lesson is that as long as you know the m, the slope, and as long as you know some point on the line, the x naught, y naught, you can just plug them into this particular equation. By the way, some of you may have seen the equation y equals mx plus b, the so-called slope-intercept equation of a line. They really are the same thing. If you have this one, the point-slope equation, then all you need to do is take that y naught, move it to the other side, and add it to the minus m times x naught. That constant together forms the b you would have seen in y equals mx plus b. All right, now what I want to do is, that's lovely, but how might I find the m in a calculus application? And the big application in calculus is the slope of a tangent line. Now that line is a tangent to the curve x squared minus 1 at the particular point x equal to 1. So now how do I get this into this particular equation? Now I'm going to put this point 1, 0 on here. Note that what this is the value x equal to 1 plugged into the function x squared minus 1 to get the y value of 0. So I have that point written here. Now, I want to figure out what the slope is. I've got the point, I need to figure out what the slope is. Well, the slope of a tangent line is the same thing as the derivative of the function at that particular point. So if this equation here is f of x equal to x squared minus 1, its derivative is going to be 2x. And so at every value of x, you're going to have a different slope, but we're asking, what is the slope at the value of x equal to 1? And so if I have this derivative, I'm just going to plug x equal to 1 into it, and so what I get is that m is equal to 2 times 1, as I was told that we're doing this at x equal to 1. Now, before I plug these into this formula, I'll note that I can modify this formula when I'm talking about tangent lines, when I also have notions of derivatives lying around. In place of the m, we're going to put just the derivative at the point of interest, in this case the derivative at 1. And in place of the y naught, well, if you know what the x naught was, in this case it's the value 1, that's where we're considering, then what is the y? It's just f of that value of 1. So if I make those two different substitutions, I'm going to get a particular equation, which is y minus now f of x naught instead of y naught is equal to the derivative at x naught, x minus x naught. You put any value of x into here, you'll get the y value out. All that remains is for us to plug in the values for our specific example. Our x naught here is 1, our y naught is 0, and our m is 2. All those things in, and that's what I get. Y minus 0 is equal to twice x minus 1.